In this question, we have a source that's emitting sound to an observer, and we're asked to find the observed frequency under a number of different conditions in which the observer and the source are moving relative to one another. Now, this question is a great demonstration of the Doppler effect, which states that the observed frequency can change depending on whether or not the source and/or the observer are moving. Now, let's suppose that the source of the sound was stationary and the observer was moving. If the observer were to be moving away from the source of the sound, then the frequency at which the observer hears the sound is going to be less than the source frequency. If the observer were to be moving towards the source of the sound, then the observed frequency would be greater than the source frequency. Now let's assume instead that our observer is stationary and our source is the one that's moving. In this case, if our source were to be moving towards the observer, the observed frequency would be greater than the source frequency. And if the source were to be moving away from the observer, then the observed frequency would be less than the source frequency. And to re-emphasize, the observed frequency is the frequency at which the observer perceives the sound to be, whereas the source frequency was the initial frequency of the sound right after it left the speaker, or the source. Things get a little bit more complicated if both our source and observer are moving. In this case, we can use the Doppler equation to calculate the exact value of the observed frequency given the velocity of the sound, observer, source, and the original source frequency. Now, the tricky part of the Doppler equation is figuring out which signs to use for V0 and Vs. Now, we define the positive direction as whatever direction the sound is traveling in. So the example I've drawn here, our sound is traveling towards the left. So anything that's moving towards the left will get assigned a positive sign. So for example, let's say that the observer and the source are moving away from one another. In this case, our observer is moving towards the left, so we're going to assign a positive sign to V0. The source, on the other hand, is moving to the right in the opposite direction of the sound, so that's going to get a negative sign. So having assigned the signs to V0 and Vs, we can plug these two values into the Doppler equation, and we end up with the equation I've written in the blue box. To correct a slight error that I made, this over here should be Vs, not V0. Vs is the velocity that our source is traveling at. Okay, so that's the formula we get when our observer and source are moving away from one another. Now what happens if they're moving towards each other? In that case, we flip the signs around because now our observer is traveling towards the right in the opposite direction that the sound is propagating in. So it's going to get a negative sign, whereas our source is going to be moving in the direction that the sound is traveling at. So it's going to get that positive sign. So now, plugging these values into our Doppler equation, we get the formula that I've written in the blue box. So this is what happens when the source and observer move towards each other. Now let's take a look at what happens when the observer and source are moving in the same direction. So the way I've drawn it here, our observer and source are both moving towards the left, or in other words, they're moving in the same direction that the sound is moving in, so we're going to assign a positive value to both. And then plugging these values into our Doppler equation, we end up with the equation that I've just boxed in blue. And this is what happens when the observer and source move in the same direction. And of note, if the source and observer were moving towards the right, then we would assign negative values to V0 and Vs instead, because they're moving in the opposite direction that the sound is traveling in. In that case, we would have plus signs in both the numerator and denominator in the Doppler equation. So now that we know what signs to use in the Doppler equation, let's take a look at the actual problem. So we're told the source frequency, or Fs, is 1 kilohertz. V represents the velocity of the sound. And we're told the magnitudes of the observer's velocity and source's velocity are half that of the velocity of sound. Let's start with part A, where we have the observer and source moving towards one another. Again, the positive direction is going to be whatever direction the sound is traveling in. In our case, our sound is traveling to the left, so anything that's moving to the left is going to get a positive sign, whereas anything moving to the right is getting a negative sign. So in this case, our observer is moving to the right, so we're going to put a negative sign in front of it, whereas our source is moving to the left, so we're going to put a positive sign in front of it. Plugging these two values into our Doppler equation, we get the following. Now after plugging 1 kHz into our source frequency and simplifying our equation, we get 1 plus 0.5 over 1 minus 0.5 times 1 kHz, which ends up being 3 kHz. And this is the observed frequency when the source and observer are moving towards one another. Now we're going to use the same approach in parts B and C. In part B, our source and observer are moving away from each other. In this case, our observer is moving to the left, so it's going to get a positive sign, whereas our source is moving in the opposite direction that the sound is moving in, so it's going to get a negative sign. Again, plugging these two values into the Doppler equation, we get the following. And from simplifying this equation, we obtain 0.33 Hz as our observed frequency, which is the answer for part B. Now let's suppose that our observer and source are moving to the left, in the same direction that the sound is traveling at in part C. In this case, because both our observer and source are moving to the left, they both get a positive sign. Plugging these values into the Doppler equation, we get the following, and then after simplifying this equation, we get an observed frequency of 1 kHz. This is because the movement of the observer, the movement of its source, cancel each other out. So the net frequency shift is 0. Now if the source and observer were moving to the right instead, the two velocities would get assigned negative values. The numerator and denominator would still cancel each other out to give us a factor of 1, and the observed frequency would remain at 1 kHz. So the observed frequency would remain the same at 1 kHz if the source and observer were traveling at the same speed in the same direction. And so our three answers are 3 kHz, 0.33 kHz, and 1 kHz for parts A, B, and C respectively.